Hello, welcome to this video looking at the February-March 2018 paper. This is paper 1 for computer science and version 2 of paper 1. The first question is talking about the different types of software, and you can see they've given us two of the software types here. We need to match these descriptions. It's quite obvious that because both are free, that both of these are going to be free to download. We just need to be able to correctly identify the difference between one that can be modified and redistributed, which means it isn't covered by copyright law, and ones that are covered by copyright legislation, which means they belong to a company. Usually we would say they are proprietary software. So in free software, the code can be modified and redistributed, so as well as the executable file, you'll also get the source code so you can edit and improve it, or make changes to personalize it to your needs. And freeware would be subject to copyright legislation. So freeware would be something like Skype. You can get it for free. You can maybe send that to someone else, a link or the software, the executable file, but you can't make changes to the source code legally. Now we're going to look at antivirus software, and we need to identify three tasks that are carried out by antivirus software. So the most obvious one is it scans files for viruses and detects and identifies them. That it constantly runs in the background to do this process. You could schedule them to run at a certain time. It can automatically update. It can quarantine a virus automatically. It can delete the virus automatically. And it will also notify you, the user, that a virus has been found and what steps have been taken. Now we're going to look at some other ways that we can reduce the risk to a computer. Or stop you getting a virus. So number one is to use a firewall, or we could use a proxy server. Do not download software or access any files from an unknown source. Do not share any external storage devices or USB pens because they could have a virus on them and you could transfer that to your device. Don't open any attachments or take care. Think, is it from a known person? Do not connect your computer to a network. Again, this is quite an extreme one of the marking scheme here, but not connecting to the internet would for sure mean people couldn't send you a virus. And again, this would limit access to the computer. So now we're going to talk about parity checks and errors that occur during data transmission. So what we need to do here is we need to figure out which one of these bytes has been transmitted incorrectly. And we know from parity checks they can have odd or even parity, which means the number of ones adds up to an odd or even number. So here we have 1, 2, 3, 4, 5, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5. So this is the only one with even number of ones, with even parity, which means the rest have been transmitted correctly because they were odd. So byte 3 was incorrectly transmitted. And again, people often get confused here about thinking it's a complicated thing to explain how you identified it, but you just have to say what you did. You went through, counted and added up the number of ones. Most bytes have odd numbers. Byte 3 has an even number, so it didn't follow the rules. Just basically what I went through. Now, we often get these 6-mark questions talking about systems and sensors. And it's even giving you the temperature range here. So the first thing we always need to mention is the sensor sending the signal to the microprocessor and there being some form of analog to digital conversion. These first two should always be mentioned in these questions for the first 2 marks. Again, then we're talking about comparing the data that you've received to a set of boundaries or a set of rules. In this case, they've identified the ranges, so I've just gone and written these out as if statements. And it's always good to mention at the end that this process is repeated. It doesn't just check the temperature once, it continually checks the temperature in the hospital all the time. So again, always mention that it's sending the signal to the microprocessor, that it's been converted from analog to digital, and then usually go into the rules that have been set up and stating that it's a continuous operation. Now we have a question about IP addresses and 8-bit binary numbers. In this case, what we have got to do is we've got to convert this binary IP into hexadecimal. So just a reminder that hexadecimal runs from 0 to 15, so 16 digits, so it's base 16, and 0 to 9 are represented as numbers, and 10 to 15 are represented as letters. So what we need to do is, when dealing with binary to hexadecimal conversion, is split it into nibbles. So 1, 2, 4, 8, 1, 2, 4, 8. So 4 bits at a time. So by putting these binary numbers into, splitting it into the 2 nibbles, you can figure it out. So this is 8 plus 1. So this is going to be, there's nothing here, so it's 0, 9. So 0 from here and 9 here. Now this is going to be 8 plus 4 plus 2, which will get us this digit, and this will be 8 plus 4 plus 2 plus 1, which will get us FE. So F being 15 and E being 14. And you can tell this is F because it's completely full, and this is 1 short from being the maximum value, which would be E. This last one I've just had to put it slightly over, so this would be 0, and this would be 1. So 1 and 0. Again, explaining why we'd use hexadecimal, it's a lot easier and simpler to remember and write down than binary. You're less likely to make an error than writing these binary numbers, and there's less digits to use, which makes it quicker to write down as well. So now we're going to look at examples of primary, secondary, and offline types of storage. Remember, primary storage is the storage and memory that the computer needs to function. So an example here would be the RAM, which stores the operating system and any data currently in use or any instructions in use, and the ROM, which stores boot up instructions and the BIOS. We can also mention the cache memory, which is small, fast memory, which is just next to the CPU, which stores the most frequently used instructions to help speed up the computer's operation. Secondary storage, we can mention hard disk drive, solid state drive, and they're used to store files and applications. Offline, we can mention CD, Blu-ray, DVD, flash memory, USB stick, removable HDD, removable SSD, and again, the same reason, these are used to store files and applications. Let me turn on the pen for this question because we need to complete this logic circuit. So this is a NOT gate. This is an OR. We have a NOT, an AND, and an XOR, which is an exclusive OR, which means this only works if I write all the binary conditions. This would produce 0, this would produce 1, this would produce 1, and this would produce 0. It's only exclusively producing the correct, a true output on the ORs. Let me just erase these very quickly. So I'll try to do my very best just with my mouse on this. So again, 0, 0, 0. 0 would become 1. So we'd have 1 and 0, which would get 1. 0 would become a 1. So you'd have 1 and 0. So this is an AND. So this would become 0. Exclusive OR. So we'd have a 1. Now we have 0, 0, 1. This would become 1, which would be 1, 0, 1, 1, 1, which would be 0, because this only works on the ORs, and this is 2 1s coming in. This one is 0, 1, 0. So 0 would give us the 1. We'd have this 1. So that would become a 1. That's fine, because it's an OR. This 1 would go here. That 1 would become a 0. This 0 would come through. So we'd have 0, 0, so this would be 0. So this would produce a 1. I'm going to erase this very quickly because it's getting a little bit messy. Where were we? 0, 1, 1. So 1, 1. This would become a 0 and 1. So this would give me 0 because it's an AND. This would give me a 1 because it's an OR. So this would produce a 1. I think I can do this a little bit quicker actually. There we go. Oh, I deleted all the ones, but you get the idea. All you have to do is write the logic gate circuits down and follow them through. I shouldn't have pressed delete all them because it's wiped this out, but you get the idea. You follow these circuits through and just write the correct answers in the working space. And this time it's very difficult, as you can see in the last question, for me to draw in PowerPoint. So what I've done is I've done the correct answer here in logically. So if we break this down into sections, we can see we have two ANDs, and we can see them coming here at the end. And we also have this OR coming in, which produces this AND and not 1 here. And we also have this coming in here, which is to do with the C and B being not 1. So let's go through this in sections. So we've got A is not 1, which is here, and B is 1 or C is 1. So that's coming there. So this represents this part of the circuit. Now we have B is 1 or C is not 1, and then that goes into that final AND. And to speed this process up, you just go through the same process we did on the last slide, and we write the correct answers, completing this truth table. Now we're going to go on to methods of transmission, and we've got these statements here, or these descriptions, that we just need to identify if this is serial or parallel data transmission. So multiple bits are sent and received at the same time. That would be parallel. In serial, it's only sent one at a time in a single direction. And bits are sent using a single wire. Data can be sent or received, but not at the same time. Again, this would be serial. Serial can be sent one at a time in a single direction, or one at a time in both directions, but not at the same time. Now let's look at simplex, half duplex, and full duplex. So multiple bits are sent and received at the same time. This is duplex. Bits are sent one at a time in a single direction. This is simplex. Bits are sent using a single wire. Data can be sent or received, but not at the same time. This would be half duplex. So think of duplex as a regular telephone call. Simplex would be like a radio transmission, as it goes in one direction to the radio. And half duplex, the most famous example would be a walkie-talkie. Okay, so now we're going to do a little bit of file size calculation. So the first thing we have to do is get the 16,000 samples per second and times them by the length of the clip, which we can just do 16 times 32, which gives you 512, and we add the zeros back on at the end. Because we're already storing this in 8 bits, this is the size in bytes, because we know that 8 bits is in a byte. So what we need to do to get this into kilobytes is divide it by 1024, and also in the exam you could also do this by divide it by 1000 to make the calculations a little bit easier. And that would give you around 500, or you could be 510 kilobytes would be the answer for this question. So just be aware of this, because we didn't have to divide it by 8 because we're already storing 8 bits per sample, 1 byte per sample. Now we have some von Neumann computer model instructions where we have the address and the contents. This seems like a confusing question at first, but it's relatively simple. We just need to realize that the program counter contains this data, so we just need to look for that on this list, because the program counter contains the address of the instruction. So state the data that we placed in the memory address, and we should know that what goes from the program counter to the MAR is the address. So don't get fooled by writing this again. It's fine. The address is going to be passed on to the next part of the fetch, decode, execute cycle. And then what data is going to be returned? This is the address. This is the contents of that address. So this is the data that's going to return from the RAM and go into the MDR. So now we have to describe the stored program concept when applied to the von Neumann model. Again, this question sounds very confusing, but let's break it down. So with the stored program concept is that all the programs are stored on a secondary storage device. So this could be a hard disk drive or solid state drive. Then data is moved from this storage device to the memory, the main memory, the RAM. And then data and instructions are stored in the same place during execution. Everything is in the volatile RAM. And they are then taken from the main memory to the registers to be executed, and they're executed once at a time. So the stored program concept means that basically the CPU and the different types of instruction have been separated out. So they're stored permanently in secondary storage. They're moved to main memory when they're needed, and then moved through the registers when they need to be executed. Now we're going to look at a file compression question, where Miriam wants to use a large high-resolution photo as a small thumbnail preview. And then we need to decide on why a smaller file would be appropriate in this situation. So we want a smaller file because it'd be easier to download. If it's a preview, it would load up a lot quicker. So it would speed things up. And let's explain how lossy compression works. So remember, we use a compression algorithm. We permanently delete data, which means it can't be reduced back to the original quality. The color depth can be reduced, and the palette, which means the palette is reduced, which means if there's a couple of different shades of red which are very similar to each other, they'll just become one shade of red instead of 6 or 7 different shades. We can reduce the resolution, which reduces the number of pixels, which again deletes data which can't be restored. And less bits will be required for each pixel, because in each box, each pixel, there'll be less zeros and ones, which means the overall file size will be smaller. Now we're going to talk about a barcode question, but it's kind of hidden in a practical situation. So you're going to give each patient a wristband with a barcode, and they're going to say what's the benefit of this? So again, it's quicker to scan rather than type the name of each patient into the system. There's fewer errors as there's no human input. And described by the barcode as red. We use a barcode reader or a scanner. We shine the light, the red laser at the barcode. The white lines reflect the light or more light. The sensor or the photoelectric cells detect the light that's been reflected back. It's fine to say sensors. The different reflections, so the different reflections from the light bars and the dark bars will be converted into binary values. And then that will allow you to read the number. The last question in this paper is asking us for 4 functions of an operating system. So there's quite a few, and I've listed them here. So it provides the interface, which allows us to load, open, install, and close software. It manages all the hardware, so anything we connect to the computer, it manages. It manages a transfer of programs in and out of the memory. So when we spoke about the stored program concept, it oversees that whole process. It divides the processing time, processor management, if we have multiple cores. It manages file handling, where things are saved and stored, manages errors, manages security, manages utilities, manages users' accounts, manages multitasking, multiprocessing, multiprogramming, and time slicing, how the computer can divide its time between doing multiple tasks at the same time. Allows you to do batch processing to process multiple jobs at the same time, or real-time processing the jobs as they happen. And that's the end of this paper.